Okay, so I'm going to just record what I do today, and then I'll have to, I'll make it available for the Zoom folk.
I mean, you could probably use
So-
that if you just put in subtitle.
Now, in Canvas, in the modules or under the assignments, I've got a limit practice sheet in there, and also I've got the key. So there's two documents in there. One is the limits practice and one is the key. I don't guess I can access that right now to show you, but you can find it. So that's what you'll practice for the test. Now, what I wanted to go over today kind of leads into what we're going to be doing next. And with these limits after the test. Let's see here. Okay. So what we're going to be doing is, let's think about this. Let's think about what would happen. We have this curve here, and I'll say this is f of x equals x squared. Let's suppose we have that. And I come over here, and here's the point. Here's the x equals 2. So this point right here is 2f of 2. Or, we could say, well, that's 2, 4. F of 2 is 4. And then let's suppose I go out here a little ways further to maybe x equals 5. And so now up here we have 5 f of 5. Or, 525. Yeah. So I have those 2 points. Now, think about if I connect these 2 points with a line. If I wanted to, I could find the slope of that line. It'd be pretty easy, because you know how to find the slope. The slope is just the change in the y's over the change in the x's. So that's 21 over 3, which is 7. So the slope of that line is 7. Yeah. And notice what we did. All we did was we just took f of 5 minus f of 4, f of 2 over 5 minus 2. Now, that's the slope of that line, but it's also called the average rate of change. Okay? So this is the average rate of change on 2,5. Yeah, the average rate of change on 2,5. And notice all it is finding the slope of that line. Because see, when we find the slope of a line, we're finding the rate of change of that line. Well, we would like to be able to find the rate of change of maybe this curve at a point. So I start off saying, well, I know how to find the rate of change of a line. That's just the slope. So I've got the steepness there. So so I just took the difference of the y's over the difference of the x's, just the old slope formula. Now, what if I do this? What if I take this line and I still have it starting over here at 2, but now I'm going to look at the slope right here at 4. So now instead of the average rate of change from x equals 2 to 5, I'll do x equals, well, the rate of change from 2 to 4. Well, I could do that as well. Now, so let me do this. I would have this up here is 4, 16. So I've got 16 minus 4 over 4 minus 2. That's 12 over 2, which is 6. So the rate of change there is 6. Now think about it. So we could move it again. I could say, well, let me move it to 3. Let me adjust this a little bit. And we move it down here to 3. So now I've got this point, whoops. So now here's 3. And I could get the average rate of change at 3 as well. Okay, so I would do this. I would do f of 3 minus f of 2 over 3 minus 2. So this would be 9 minus 4, which is 5. Okay. So what I'm doing is I'm using smaller and smaller intervals. Now let's think about these intervals as being h, or delta x. So on this first one, the delta x was 3. On the next one, the delta x was 2. And on this one, the delta x is 1. The h is 1. You see that? Whereas I just keep adding these. So for example, here's what we looked at. We looked at f of x plus, 2. We looked at 2 plus 3 minus f of 2, well, over, and it was 3, right? That's the distance. Okay, so here h was 3. Then we had f of 2 plus 2, h of 2. So you can see how this works. In other words, the change, the delta x, or the h, it's on the bottom, right? So generally what we have is we have f of x, we have 2 plus h minus f of 2 over h, right? Y'all see that? Okay, now I want to open my calculator. Okay, now, so what I've got here is notice I've got 2 plus, instead of plus 1, I've got 2 plus 0.9, right? Minus f of 2, which is 4, all divided by 0.9. And remember, we had 7, 6, 5. That slope was changing as I made this smaller and smaller h, right? Now, let me change that some more. Let me change that 9 to a 0.5. And you get 4.5. In fact, let me do this a little differently. Let me just make this x. Let me streamline it a little bit. And let me, I'm going to make delta x smaller and smaller. So let me just do 0.1. I'll store that in x. And then let me calculate it over. Okay, here we go. So look, we got 4.1. Y'all see that? Now I'm gonna make the 0.01. I'm gonna store that in x. Now we got 4.01.
So there's an asymptote of 4.
Yeah, it looks like it. So look, think about it. We're evaluating this limit. 2 plus h minus 4 all over h. And we're letting h get smaller and smaller and smaller. So let's do this. Let's say 0.00001, and I'll store that in x. Okay? And then I'll go back up here and grab this thing. Evaluate it. Look, 4.000001. Okay? So here's what I want to point out. We've got this function, and we've got this 2 right here, and we've got this, where this point, right, so here we've got the point 2, 4, and here we've got the point 2 plus h, f of 2 plus h. right? Okay. And down here is 2 plus h. And I want to get the slope of that line right there. Well, it's going to be it's going to be f of 2 plus h minus f of 2 over 2 plus h minus 2, that's just h. That's the slope of that line. Now what I can do, I found, okay, when I let those 2 points be far apart, I had x equals 2, x equals 5. When I had those points far apart, the slope was 7. Then I moved the x's closer together, and I found the slope to be 6, and then 5. And then I started looking at, well, what happens if I'm between 2 and 3? 2.9, 2.01, 2.001, and so forth. And I let h get smaller and smaller and smaller, and we found that the slope looked like it was approaching 4.
Yeah.
Okay? So what we looked at graphically when thinking, well, maybe I can show it algebraically. In other words, maybe I can evaluate this limit. It looks like the smaller h is, the closer we get to 4. So let's try that. Let's see how it works. We've got the limit as h goes to 0 of 2 plus h, right? Because we're dealing with the square function. Now, let's see how this works. We've got the limit as h goes to 0. Now I'm going to expand that out. So we get 4 plus 2h plus h squared minus 4 okay. And this one cancels with that one. And then look what we can do. We can factor out an h. So we have the limit and by the way, this is, that's it. Wait a minute. You know what? This should be 4 right here. I'm sorry. I expanded it out wrong. There we go. Sorry about that. See, when I expanded this out, I forgot I called it 2h instead of 4h. Now these cancel, and if I let h go to 0, I just get a 4. Now, so that's a pretty cool thing, because what we started off doing, we started looking at the average rate of change, the steepness of a line between 2 points. But then we took note, as those lines, as we get closer and closer and closer, as those 2 points get closer and closer and closer, what does the slope of that line tend to? What is the limit of that slope?
It's going to be whatever the y value is of the point that you're getting closer to, or the point you're using to get closer to the y value.
Yeah, so well, what do you mean?
Like you're getting closer to 4 there, the y value for that one, or at least I guess getting closer to x or not.
Oh, well, this one was
See,
getting
like,
full.
the x then is 2, 4. And this is in his case, I guess. I don't know. That's what it
Mm-hmm.
seems like.
Yeah, in this case. That's right, in this case. Now look. So let's think about what we've come across here. What we're saying is we can play this game where we've got a line. Okay? And I'll just call this x, and this is x plus h. Those 2 points. I can get the slope of that line. The slope of that line, because this is x plus h, f of x plus h. This is x, f of x. This is a secant line. I don't know if it has anything to do with the secant in trig. I don't think it does. But this is they call this the secant line. It goes through the graph in two places like that. And we can find the slope. The slope is just f of x plus h minus f of x over h. That's the slope of the secant line. And that will tell us the average rate of change. So if that yellow graph were distance, for example, then the slope would be the average velocity, because you're taking the change in distance over the change in time. So for example, if you go 120 miles in 2 hours, you know how to calculate your average velocity. 120 divided by 2, 60. You average 60 miles an hour. So it's the same thing here. If our distance is described by this yellow curve, then the slope of that line, the change in distance over the change in time, see, change in distance over the change in time, that would be our velocity, our average velocity. But let's suppose we have a situation where we want instantaneous velocity. We want the velocity at x.
How fast we're going.
Well, that's where we let h go to 0, and then what we have here is, a tangent. We have a line that touches the graph at exactly that one point. It touches the graph at exactly that one point. Okay, do y'all see that? Now, I was gonna show you something on Desmos, but I don't have to. I can show you with the calculator. What we found is the slope of that line. We found the slope of that tangent to be equal to 4. That's what we found. Okay. So what we have now is we have a curve, f of x equals x squared, and we have a line that's tangent to it that has a slope of 4. Now, of course, it passes through this point 2, 4. Right? So we have a line that touches the graph at the point 2, 4. So if I wanted to write the equation for that line, I could take y minus 4, y minus y naught, the point slope form of a line, equals the slope times x minus x naught. And the x naught is 2. Whoops. Y'all remember that? The form of a line?
Yes. Oh, yeah.
Yeah. That's the way we can write the equation for a line if we know a slope and a point. This point is x naught, y naught, and the slope is m. So there's the equation for that line. Now let me get it ready so I can put it in my calculator. This is y equals 4 times x minus 2 plus 4. That's the equation for the line that's tangent. Now look at this coolness here. Let's put this in. I'm going to put in x squared. And I'm going to put in that formula. 4x minus 2 plus 4. And let me just do a zoom. So you notice we've got the curve, x squared, and we've got the red line. That's the tangent line. Now, I want to do something here. I'm going to zoom box, I guess. Let me come over here. Now what I'm doing is I'm zooming in on that point of tangency. I zoomed in a little bit. Okay. I'm going to zoom in. feel like a jackass. Okay, now, look at that. See how I'm zooming in there, right? Okay? Now, right there's the point of tangency. We don't have it, I need to go back here. Oh, there, a little more. No. Whoops. Okay, now I'll zoom in again. Now, notice as we zoom in, the more we zoom in, the steepness of our line and the curve, they look exactly the same. So here's the thing, if you zoom in enough on this, and let me just turn off the line. Okay? This is the graph of f of x equals x squared. We have zoomed in enough where all we see is a local linear situation, local linearity, right? So we zoom in here enough and it's just linear. That's all we see is a line. But it's because we're zoomed in so much. But if we can zoom in that much and see a line, think about the tangent. The line that we found the slope of that line was 4. Well, if we know the steepness of that line, we could make a connection to the steepness of the graph at that point. Because there's no difference, right? Because here is the curve. Let me turn off the curve, and here, well, I'll turn them back on, both of them together. They look exactly the same. So, if you're talking about, we know how to find the steepness of a line, the slope formula. But it turns out we can use that together with limits to find the steepness of a curve at a given point. Because if you tell me that that curve, that line has a slope of 4, you go over 1 and up 4, the curve has the same thing. Right? They look the same. And the more you zoom in, the more pronounced that will be. So, what we found is a thing called the derivative. We have this function, f of x equals x squared. And we want to find a way to measure. So this is a machine, f of x equals x squared. You put in an x, it will give you an f of x. If you're talking about distance, you put in a time and it will give out a distance. We want to find this, f prime of x. That's also a machine. And that machine, you put in the time and it will give you the velocity. It measures the rate of change of x squared. It tells you the steepness. And we get that from this thing. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. That right there. This is the derivative. It's called the derivative. It's the derived function. This measures the instantaneous rate of change at a point. So we're not limited, to just finding the average rate of change. We can now find the instantaneous rate of change at a point. So when you were studying slopes, back in Algebra 1, or whenever you studied them, you didn't realize, well, you were studying calculus, you're finding the derivative. But what you were doing was you were studying calculus just with lines. Now we're going to expand that to say, well, let's use that, let's build on it, and now figure out how we can measure rates of change just in general, for general curves. See? So this is why, when we study calculus, we are really studying, we're stepping our way through and noticing, well, this is how humans' knowledge evolves. We start off with something basic, and then we use that and build on it. So the slope of a line, then we study limits, and we put that together, and we can study instantaneous rates of change. So I want to find the formula for the derivative for this one. So here's what I'm going to do. I'm going to do the limit as h goes to 0 of x plus h squared minus x squared. See? F of x plus h is x plus h squared. You'll see that? Now, so how would we do this? Remember, how do you evaluate that limit? Come on now, you know. Don't be shy.
Just break it down. Like,
You expand it out, together like terms? Yeah, y'all know. Y'all are shy. Okay, so we get x squared plus 2xh plus h squared minus x squared. Yeah, there you go. Huh? Yeah, those x squareds will cancel.
Then you can pull out an h.
Yep, that's right. So you have the limit as h goes to 0 of h, 2x plus h over h.
Cancel those. It's 2x plus h.
Look at that yellow Cavendish. Does that make you hungry for bananas? Every time my grandson watches Minions, he has to go in the kitchen and get a banana. Have y'all seen Minions? Okay, because they eat a lot of bananas. So, the limit is 2x. The limit is 2x. So what this is a very powerful function here. It will tell you the slope of tangents for any point on that parabola. You give me x equals 3, I'll plug it in there and the slope is 6. X equals 10, the slope is 20. You can have negative slopes. You give me x equals -1, slope is -2. Okay, do y'all see that? So, we have this difference quotient. We have this difference quotient. F prime of x is equal to the limit as h goes to 0 of f of x plus h. Now, over h. This is what a derivative is. It's the limit of the difference quotient. If anyone ever asks you what's a derivative, it's the limit of the difference quotient. It's also the slope of a tangent line at a point on a curve. That's what the limit of the difference quotient is. And we use it to measure change, the rate of change. And that's what we do with it. Now, here's what we did. We used the difference quotient to find this. We had the function x squared, and we found the derivative to be 2x. That's what we found. We derived a function. We derived a formula. Now, let's do this. Let's suppose that we've got the square root of x, 1 over x, and then let's do x cubed, whoops. Let's do x cubed and x to the 4th. Let's see if we can find the derivative. So what you need to do is you need to set up the difference quotient for each one of these. Now, you might say, well, hey, we got a test coming up. Let's review. Well, we are. We're those limits, evaluating those limits is going to be on the test. So anyway, take a minute and try to set up the difference quotient for the square root of x. And then, there's the trick to going through and simplifying. Okay, so in this first one, we've got the limit as h goes to 0 of the square root of x plus h minus the square root of x. Okay, now remember we had a trick for this. Remember what that was?
Yeah, you want to find out the reciprocal.
Yeah, the conjugate.
Conjugate.
Yeah, I got you. I knew what you were talking about. So the limit as h goes to 0, so let's see here, x plus h plus minus. Okay, so that's what we do, that's the trick. Just multiply by the conjugate. And then what you get up top okay, so what you get up top is you just get x plus h minus x Now, what you get after that is 1 over 2 square roots of x. Does everybody see that?
Yeah.
Because if the h's cancel, then I put a 0 in, I've got the square root of x there and another one there, 1 over 2 square roots of x. Okay, so we found this one to be 1/2 x to the negative 1/2. You might think, why do you write it that way? That's the same thing. Okay, any questions about that? So the next one we're looking at is the 1 over x. So we've got the limit as h goes to 0 of 1 over x plus h. There's the setup for that one. Now remember, there's a trick to that one as well. Okay, so remember the trick on this one is we multiply by the common denominator. Okay, so this is 1 over x plus h. So I just multiply by x times x plus h. I multiply by the product of, the extra denominators. And what happens when I do that is those extra denominators get canceled. And then if you let h go to 0, what you get is negative 1 over x squared. So what we found here is we're finding all these derivatives, these derived functions that measure rates of change for these functions. And if I go back up here, I've now found this one, and this one is negative x to the negative 2. That's what it is. Okay. Now we want to try x to the third and x to the fourth. Now remember, those are where you expand out the binomial, either using Pascal's triangle or that theorem that I gave you. When you expand out those binomials, you've got to get the exponents and the coefficients. Those are the two things. So we're doing x cubed and, forgot to, so there it is expanded out. And immediately, once you get that done, you notice things cancel.
You got x, and then you can factor out.
Mm-hmm. So what is that one? If you let h go to 0, all the h terms are 0. What do you got? Yeah, that's it. That's the ticket. 3x squared. Okay, now, one more on this. Let's try x to the fourth. So we've got f of x equals x to the fourth. And there's the initial setup. Now remember, one of the suggestions I made was you can use Pascal's triangle to generate those coefficients. See, there's to the fourth power, 14641. There it is. So we got it all expanded out. And always you're going to notice these kind of things will cancel. And then, so we can factor out an h. Hey, what did I do? This should be cubed right there. Ah, I messed up. That's important. 4xh squared. So if you let h go to 0, replace all the h's with 0, you're just left with 4x cubed.
Yep.
Now, let's just take a minute and think about what we've found here. Now remember, all we're doing is the slope formula and letting the points get infinitely close together, and we're ending up with slopes of tangents. So let's see what we've got here. Let's just look at this. We had f and f prime. This is read f prime of x. So let's see here. We had x to the negative 1, right? That's 1 over x. And we found the derivative to be negative x to the negative 2. Then we did x to the 1/2. We found that one to be 1/2 x to the negative 1/2. We did x squared. We found that to be 2x. We did x cubed, and we found that to be 3x squared. We did x to the 4th and found that to be 4x cubed. Right? Now remember? We did all those, right?
So it's
So, what now? So what do you think would be x to the 100th?
X to the
Yeah, there we go.
Wow.
In fact, what we have is, we use these limits. We have the definition of a derivative. And then we go back and we use that definition and we discover things. Like, one of the things we discovered here was if you have a function of this form, x to the alpha, alpha is some real number, it looks like the derivative, f prime of x, is going to be alpha x to the alpha minus 1. That's the way it's looking. Now, we're going to prove that to be the case when we really get into the derivatives next week. But this kind of gives you an insight. What we do in calculus, we start off with the limits. And then we start exploring, we use those limits to explore different things, like slopes of lines. In fact, we use those limits to finding, how do we find the slope of a tangent? And the idea is, if we know the slope, if we know the steepness of a line at a point on the curve, then we know the steepness of that curve at that point.
Yeah, we know the instantaneous speed.
Right, right. So if we're talking about the curve being distance, well, the slope is the average velocity, and if it's a tangent slope, then it's the instantaneous velocity. And there's all kinds of implications in this. I mean, the slope of a line is very powerful. So we can calculate how fast the body is metabolizing a drug. Someone gets a drug, well, how much drug, when will the drug be out of their system? Well, what is the rate at which the body is metabolizing it? Those are all calculus type problems. And it goes back to the slope, the difference quotient. Okay. We use that difference quotient to study a lot of things. But it's a limit. That's all it is. So if someone says, what is the derivative? It's the limit of the difference quotient. Now, I can't, because the internet's down, I can't show you. In Canvas, I put in there those two things. I had the practice, limit practice, and I have the key to it. So I have them all worked out. The key is like 10 pages long because I try to work it out in detail. But what you'll need to do in preparing for the test is study that thing. Go over those sample problems, and anything that you're at all concerned about, you let me know, and then I can give you more practice, or I can go over it with you. Okay? But there are several problems on there. If there's anything that doesn't make sense, that's where you have to say, I know what to ask about this. The test is not, it's not going to be anything where I try to surprise you or give you, I'm not going to try to cause you vexation of spirit or anything. It's just if you know what we've been doing, you'll do great. Yeah.
So that limits practice is the only thing that we need to practice, or is there other stuff that we also need to do?
No, what's on that practice sheet is what you need to know. Now, what we did today in evaluating these limits, you need to know how to evaluate all those types of limits. like, the square root of x plus h minus the square root of x over h. You need to know the procedure for evaluating those. So what we did today was just kind of practice. Remember the tricks. You plug in. Okay? So if you plug in and you get 0 on the bottom, but not on top, you've got an asymptote. If you get a 0 on top but not the bottom, the limit is 0. If you get 0 over 0, then you're going to factor and cancel. You're going to multiply by the conjugate, multiply by the denominator, or expand out and cancel like terms. The tricks. In other words, there's a finite number of tricks. Okay? Any questions? Okay. Yeah. So I think that'd be good for today. I don't anticipate you having any trouble with the test. How many people do we have working from home? Is this a high flex class?
Yeah.
It is?
Probably
Okay.
about that, probably.
Okay. What I'll probably do, I'll probably give you the test Monday, and then you turn it in the next day. So it'll be one of those things where you don't work on it in class. We'll just have you work on it and you bring it to class Tuesday. Yep. Any questions?
So are we coming to class Monday?
Yeah, you'll come to class Monday and we'll cover stuff, but you'll turn in the test Tuesday. Okay. Yeah. Okay.